Welcome to the exciting world of composite materials. Today we'll be discussing how we can optimize composite structures. Given a structure, given the loads applied to the structure, can I come up with the ply angles, the stacking sequence, the thickness, the number of plies, or maybe I have a list of materials. Which materials can I use in my design to minimize the weight, give me the performance I need? That is the idea behind using composite structures, is to give you that ability to tailor them to minimize the weight. That is advantage over metals. In metals, you're kind of stuck with an isotropic type material. So there's little you can do, like maybe change the thickness or change tapers. But with composite materials, you gain that additional flexibility of changing ply angles. And so if you were to use a quasi-isotropic laminate, that plus minus 45090, that's going to give you very limited ability to optimize the composite because it acts isotropic in that plane. It's called also black aluminum. While there's a lot of software out there that can do this for you, such as Hypersizer, today's lecture is intended to give you background onto the optimization of composites, number one. Number two, for you to develop that intuition. Say I have a huge amount of load applied in X direction, but very little load applied in the Y direction. So it should be clear to you that I need the 0 degree ply to be oriented along the highest loading direction, and maybe I need less plies so that those plies take the load in the other direction. If I have shear loading applied, then perhaps I need angle ply laminates that can be able to take that load. But the idea here is for you to develop the intuition, to apply the intuition. Now, one of the things I want to mention is that just because you came up with a stacking sequence for that design, it's important to consider how you should place the plies. You don't want to place the plies in a situation where it will cause delamination. So it takes a lot of work, a lot of understanding of how composite works. But today is a good stepping stone at really understanding the benefits composites can offer. So why we don't go and dive into this? It's an exciting class, I think. One of my favorite things is designing composites. So let's dive in. So let's dive into the fundamentals of how optimization really works. So in basic Newton's law method, and Newton's method is one of the topics that we need to learn to understand how the optimization algorithm we'll be discussing really works. So say, for example, you have x cubed minus 8 equals 0. We want to solve for x from this particular equation. So the idea then is to set this to a function of fx and then find x such as fx is 0. So we know x equals 2 is a solution, but we want to be able to do that numerically somehow. To accomplish this, what we can do is assume x is a guess, but that's near the solution. If that's the case, and fx is close enough to 0, we can do a Taylor series expansion about the nearby solution. So we have x plus dx, and the idea is that x plus dx is the actual solution to the problem. So then when I apply Taylor series expansion to this, I get fx plus f prime x dx. Now, if x plus dx is the real solution to the problem, then f of x plus dx must be equal to 0. And this x and this x and this one here is basically nearby the solution. And since this is 0, we can then solve for dx. And so here at the bottom, you can see I can put a guess here, and solve for dx. Once I find this dx value, I can correct my old guess by adding to dx in this manner. And that will give me x new, and that x new can be checked to see if that got me close to the solution. And if it didn't, then I can use x old as x new, and then repeat this whole calculation in an iterative manner until the function f becomes 0, at which point I really have found the value x new that makes that equal to 0. And that is going to be true. So what are the key equations here? As you can see, is going to be this dx calculation and then updating the guess with dx. And then once you do this updating, you can find a new value of x. And if it's not going to, if that doesn't give fx equals 0 with that value of x new, then you have to basically start over, but now use x old as x new, and then repeat the process in an iterative manner. To illustrate, in this example, we have x old, which is my guess, and it's 6 as the guess. I find fx old, which is 208, so it's 6 cubed minus 8, 208. F prime x old, that's 108. 3 times 6 squared, that's 108. Then I can calculate dx, which is the correction that I need. And notice how I have f prime here, and that's a gradient, that the derivative of that function. And you can see here again, minus 1.92 as a correction. Add that to the x old to get a new x new, 4.07. And then that value is used as a new guess. And then start over with the process. I get an updated value of x new, use that again as a guess, and until this function f approaches 0. And notice how f is also the error. So here, for value of 6, I get an f of 208, but I really want this to be equal to 0. So you can see here clearly how that function f is dropping to 0. And as it drops to 0, the error is becoming smaller and smaller, and I'm approaching the right solution for x old, which is 2. So that works really well. And now to illustrate this in Excel, we go here, and we've implemented that here. X old is 6, fx old is b cubed minus 8, b3 is that cell there. Then we have fx old prime, which is 3 times this cell squared, and then dx, which is a ratio of these two negative. And that you can see that there, that's a ratio right there. And now you can correct x old by adding to that. And that's what was done in this cell, B3, cell B3 plus E3. And that gives me the value. So now I can go ahead and use this as my guess, and then repeat the process until x is converging. And in this case, it converges to a value of 2, and the error has dropped to 0. The good news is that we can do this also with the algorithms available in Excel. So I can go to File, Options, and then Add-ins. And here you can add the solver add-in. Once you do that, you can go to Data, and you're going to have a new icon that says Solver, top right. And then you can click on that solver. And the idea here is that I have defined an objective function. The objective function is x cubed minus 8. And what I really want to do is I want this to be a value of 0. So I set this objective function of f14, cell f14, to a value of 0 by changing the design variable. In this case, the design variable is x, and right now the guess is 3. And then we can now use GRG nonlinear if you want. I'll be covering GRG nonlinear later. I hit the solve button, and what I've done is then found that the value is 2, the design variable. There's other ways to approach the problem for this particular situation. One approach is that this function f also represents the error. So what I could do is, what I could do now, let me see if this works. We could now take, I want this value of f to be 0, but another approach is to minimize the value of f, so the lowest value it can reach is 0. So if I put a value of 10, I get an error of 992. I want to really minimize that error. What I can do is make this a square, okay? And this will always be a positive value in that manner. And in that manner, this error is pretty large. And what I can do is minimize it now. So F14 can be minimized by changing the design variable here. And notice as this approaches a value of 2, 2 cubed minus 8 is 0. And so I have, in fact, minimized it. Instead of having to equate it to a value. So by minimizing this error, I have solved also for x, and this is called a minimization problem. So let's hit solve, and you can see here that I was able to basically solve the problem by minimizing this objective function. We call this objective function, and this one a design variable. So two ways that we've approached it, but both work relatively well. I could go now to a Newton's method for n equations. I can take n equations that I may have, and I have n design variables. It could be nonlinear in nature. And the idea is how to do this in a automatic way, numerical way. Very similarly, we're going to assume that x is a neighboring solution, x plus dx is the actual solution. If that's the actual solution, and f is a vector of all these functions, and x is a vector of all the design variables, that by correcting it by some value of vector, by correcting it by a vector of quantities, I'm able to find the value of x that makes f equal 0. And so I can do a Taylor series expansion about that, x, the neighboring solution, and so I have fx plus the gradient of fx dx. And now I can solve, and notice how the gradient of f is the Jacobian. Here, I made an error, but it will be the derivative of f1 respect to x1, the derivative of f1 respect to x2, derivative of f1 respect to x3, and so forth. The second equation will be derivative of f2 respect to x1, derivative of f2 respect to x2, derivative of f2 respect to x3, and so forth. So this in general, the formula is derivative of fi respect to xj, and we will consider this to be an n by n Jacobian, which is the size of the matrix is driven by the number of design variables. And since we have found the solution, supposedly x plus dx is the actual solution, set this equal to 0 and solve for dx, which is a correction. So then I have to invert this n by n matrix, which is this one, and solve for dx, and I will get this now. So with that correction dx, and notice how I can add that to my guess to get the new value of x. And so in this manner, I can, now with a new value of x, if that does not give me the actual solution, I can use it as an old guess and start iterating until I get the actual answer to the problem, approximation to the solution to these equations. Now notice how this is the gradient of f. That's going to become very important because that's the direction that allows dx to decrease. The gradient of f has to be positive definite for dx to decrease, and that's the way this should work. Now let's look at how this was implemented, how this can be implemented in Excel through an example. Here we have two equations, and we want to solve these equations for x1 and x2. This is a very nonlinear problem. In this example, the Jacobian can be found fairly readily as the derivative of f1 respect to x1. That gives me 4 and 4 x1. There you go. And then the derivative of f1 respect to x2. That gives me minus 6 x2 squared. And then for the second equation, I have the derivative of f2 respect to x1, and then the derivative of f2 respect to x2. Feel free to pause the video to make sure you're able to get this. Now I'm going to go ahead and go to Excel and show you that, in fact, I'm able to find this as a solution. So why don't pause the video, think about how that can be put together. So I have given you this Excel file, and you can check it out. But here what we've done is put the all guess here. And these functions that we have here are the objective functions. And notice how these have to be equal to 0 for us to be able to find the actual solution. So this actually will be the error to the problem. And so here's the first equation, the second equation that we showed you in the PowerPoint. And here we've calculated Jacobian to the problem. So what we've done is incorporated the PowerPoint equations in here, and we then find the inverse to the Jacobian. And so I'm going to bring these equations in so you can see these are the two equations. This is a formula we want to incorporate, which involves the inversion of this Jacobian. And so that was done here in Excel with the M inverse command. You can invert this Jacobian right here. Notice that it requires the values of the guesses to be able to calculate the Jacobian numerically, then invert that using M inverse, then perform this multiplication right here, the J times the J inverse times this vector F, this vector, which is the error. When we do that, we get these two values for the correction dx. That's this correction here dx. We take dx and add that to the old guess, correct it and find a new x. So here's the dx, add it to the old x, guess the new x. Now take the new x and use it as the old guess, and then repeat the process iteratively until you can see here the error is dropping and we have found the solution. You can see here the solution is not changing very much, and we've actually gotten a solution even in the third iteration. We could approach the problem using the solver, and the idea here is that if I take this function f1 here, this function f1 here, for some value of x1, if it's not the actual solution, then this is going to give me an error. It's not going to be 0. And function f2 is the same way. If I don't put a value of x1 and x2 that's the actual solution, then this will give me an error. The goal there is to minimize this error. How I can do that? I can calculate the RMS. So say I have the two design variables, x1 and x2. I have the objective functions, f1 and f2. What I want to do is minimize the objective function, so I can take the RMS, square root of the error number 1 squared, the error number 2 squared, square that, and figure out the solution to the problem. And so here I'm going to start with the same values we started as the guess in the previous problem. Right here, we started with 0.5 and 1. So what I'll do now is, again, I go to data. Now that I have installed the add-in, so go to data. We want to go to solver. And what I want to do, I already did it for you, but here is R8. That's this cell. I want to minimize this R8 by changing the design variables T2 and T3. And I can now hit solve, and hopefully this will arrive to the actual solution. And it did. You can see here that 0.6177 is exactly what I got with the Newton's method. But now I have approached this problem from the optimization perspective, trying to minimize that error to be able to find the values of x that make that happen. You can see here that we were able to minimize the error relatively well. I mean, this is close to 0, so we've been able to accomplish that. So now, why we don't go back and graphically look at this problem? Graphically, I have the two equations being plotted, another equation which transverses this one here. So we have two solutions where that happens, and you can see here that we found this solution right here, 0.06, and then that's about 0.7. So that solution corresponds to this point. Can we ever find this solution? That may not be always possible. And to illustrate that, let's go back to the optimization problem. You can see here that if I select a value closer to that solution, which was about 1.5, and then it was close to negative 0.5, the question is, can I try to minimize the error and find the solution that was near this point, this intersection? And it's possible that we may not be able to do it. We'll see if we can. So we hit solve and see if that happens. And you can see here that the error was not minimized to 0. There could be various reasons, but one reason is that we're not able to converge it to make that happen. If we were to use our Newton's method here, and I use the same initial values, 1.5 and minus 0.5, you'll see that the error is only increasing. So we're not able to achieve a solution. And so it really comes down to guesses, making the right guesses and see if we can get there. We could try, for example, more like a value of 1 and -1 to see if the algorithm wants to converge. But the point I want to make anyway, even if this does not converge, is that it's not always possible to get the most optimal value with these algorithms. And the question is, can I really, did I reach the global minimum? Did I reach the minimum value for my problem? And that's a very difficult problem to really, that's a difficult question to answer. But that is one of the disadvantages of optimization, is not always being able to say, hey, did I reach a global minimum? Or did I reach a local minimum? Or did I reach anything at all? In this case, it's unlikely we're able to achieve much, but the point being is that optimization can be a very difficult problem. One approach that people have used is to use something called a line search method using Newton's method. So the idea here is, as long as the Jacobian is positive definite, dx will always decrease, and is going to go in the downhill direction. But it's not always possible to make this happen. And sometimes when you have a gradient that causes a huge correction to your solution, it may cause even bigger problems where you get oscillatory behavior, you may not get to the actual answer to the problem. And so it becomes extremely important to study the problem using line search algorithms. In optimization problems, instead of running through this solution, we will want to then use an alpha in front. And sometimes we want the alpha to be less than 1. But the idea is to kind of slowly get to a solution in case the gradient sends me in some other direction where I may have a better global convergence. So that is one approach that is used. In this case, you're also minimizing respect to alpha. So your objective function is also minimized with respect to alpha. Here also, I want to point out that there's a special case where gradient of f is taken as the identity matrix. And in that manner, you have now fixed the direction of steepest of descent. So your gradient has been fixed to 1, basically, and you're minimizing relative to alpha. And the only thing influencing the solution now is the error, the drive to minimize this error by selecting alpha. And so that is one approach that's used that needs to be considered. You can have the idea of minimizing an objective function. So you can use a line search in combination with Newton's method to really minimize that objective function. To do that, the question becomes minimize the function f, but relative to the variables x and now the variable alpha. So this is equivalent to really determining the line search parameter such that the gradient of f relative to alpha equals to 0. F bold here is a set of objective functions we're looking at. Now note that this is not very different from when you, in calculus variations, were given a function, say the function was 4 plus x squared equals 0. And I want to find out where the minimum occurs. You will then take the derivative of f respect to x, and then you get that's about 2x, and 2x equals 0, so the minimum occurs at x equals 0. Very similarly here, we're minimizing this objective function relative to alpha now. And so the Newton method, the line search method, and additional methods are typically used to determine variables to optimize a function. So that takes me to the generalized reduced gradient. One of the most robust optimization methods available that are readily available and implemented in software such as Excel even and MATLAB. Is versatile, good for unconstrained or linearly constrained problems, but also works well for nonlinear constraint problems. You can utilize existing simulators that employ Newton's method. And the idea here is that the equalities have to be satisfied at each step of the algorithm. So if you validate one of the equalities, then you're going to have to kind of revisit the problem. And so let's learn this method. This method has a lot of merit in the way it's applied, um, and there are books that talk about this method. Um, we have here the idea of minimizing the objective function. So I want to minimize this objective function subject to a set of constraints, and the set of constraints could be inequalities like this. The approach that we're going to take is turn this positive into a negative sign by multiplying by minus. And then what we're going to do is add non-negative slack variables to each inequality constraint. And the idea is to convert each of these inequalities into equalities. So by turning this into a negative and adding a positive value of a slack variable, I'm able to make that into an equality constraint. The problem is that I don't know what the slack variables really are, but that becomes a variable. And secondly, this now is turned into equations. So let's call this equation here is GI, equation number 1, 2 through N. M, because I have M inequalities. And so this becomes your constraint minimization problem. Basically, minimizes objective function subjected to this set of constraints. Now note that the design variables continue to be x1, x2, x3, blah, 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 but we are now subject to this constraint, and S now are slack variables that need to be addressed. So this is your constraint minimization problem, and it involves the usage of Newton's methods and line search algorithms. So we want to define a vector Z containing variables, design variables and slack variables. So these are the design variables, and these are the slack variables. I'm going to use these, take these variables and put them into a single vector Z. So now the optimization problem is to minimize f, the function f, relative to z, subject to a set of constraints that I have defined already through here. And again, these are inequalities plus the slack variable that are non-negative. And so with that information, now I can find the gradient of f, which is what will help me minimize f. And when I do so, I have gradient of f relative to x dx plus the gradient of f relative to s ds. And then the gradient of g is 0 because this is 0. And so the gradient of g is the gradient of g respect to x dx plus the gradient of g respect to s ds. That's equal to 0. I can solve for ds and get rid of the slack variables. And by solving for ds, I can put in the top equation. I can plug it into top equation, and then I'm left with one equation alone. This is exactly what we have done. Solve the second equation for ds. Feel free to pause the video and do it yourself. We solve for ds and plug it into the first equation. So solve for ds here, the second equation, plug it into the first equation, and once you do that, you get the formula for df, the gradient of f. This right here is called the generalized gradient, and that is the search direction. In essence, that is the search direction that's going to allow me to decrease, to minimize the function, the function f, the objective function f. So to determine the new x with the old guess x, what I want to do is add the idea of this line search parameter alpha with the search direction g, r. So this one is called the generalized gradient. So the generalized gradient is found, and that's the direction that's going to help me minimize the objective function. And alpha is going to temper the amount that I am reducing that generalized gradient. So this can be determined by first finding alpha and minimizing the function f relative to alpha. And if any of the constraints here, any of these constraints g is violated, then I have to recalculate alpha until the constraint is met. And so that fixes the value of alpha, and then I can proceed with the minimization problem. GRG is a lot complicated than what I have explained here, but I have given you the top level perspective on how to approach an optimization problem using GRG. And I will illustrate this through an example. Now, nonlinear optimization problems using the GRG method can be found in a paper written by Leon Lasdun. So I encourage you to pause the video, download the paper, give it a quick read, and kind of get an idea of what I have been discussing. So let's apply this to an example step by step manually, and then I'll go and step into Excel. Let's solve it there, and then from there I'm going to take and apply it to a straight into a composite example, because that's what we're trying to do, right? We're trying to come up with the design variables, and that can be apply thickness, apply angles, materials, such that I have an optimal design. And in composites, the optimal design is to minimize the weight, but yet so that the structure can take the loads that will be subjected in service. So that's really what we're trying to accomplish. But I first have to cover some fundamentals of GRG, which I think are important in the understanding of how the software works. It also is important to understand that these examples will provide us with some insights as to the fact that sometimes we do not know whether we have reached the most optimal solution for the problem. So if I want to minimize this function f, which has two design variables, x1 and x2, and the function was x1 squared plus x2 squared plus 4, minimization of this function relative to these variables can be visually looked at here. If x was a value that was negative, f can only go up because a negative value squared only adds to 4. If x was positive, you're still going to increase the value of 4 to a higher number. So I'm not really minimizing. My only solution is really x1 equals 0, x2 equals 0, but it violates a constraint. So 0 plus 0 is minus 0.2. It's not greater than or equal than 0. So I have to figure out a different way of doing this. Now, clearly here, if I select x1 as 0.1 and x2 as 0.1, I can meet this criterion and yet minimize this constraint. So the question is that the solution to the problem? Note how the second equation is not violated by selecting x1 as 0 and x2 as 0. So the first step is to convert the problem into a problem where we can apply the generalized gradient problem. And so I'll add a slack. I'll first multiply by minus sign and then add a slack variable S1 and S2. And S1 and S2 can only be positive values. So now the optimization problem has been turned into minimize this function relative to these two constraints problem, these constraint equations. So in other words, find x1, x2, then minimizes f, but yet find s1 and s2 so that I don't violate these constraints, and I can satisfy the question, which is to minimize f. So s1, s2, x1, x2 are unknown. In this example, the generalized gradient actually reduces quite a bit because f does not contain, the function f in this example does not contain slack variables. As a consequence, the gradient of f relative to s is 0 and this whole thing goes away. So I'm left with the gradient of f relative to x, and I can evaluate that readily. So the derivative of f respect to x1, the derivative of f respect to x2. In our example, the derivative of f respect to x1 is 2x1. The derivative of f respect to x2 is 2x2. And you can see here that gives me the generalized gradient as 2x1, 2x2. This generalized gradient tells me in which direction I am trying. It gives me a search direction. And the search direction is the one I'll be using to minimize the error or the function, okay? So how do I continue? So the new predictions are obtained as follows. So if I have an old guess, what I'll do, I have plus alpha times the search direction GR, and which we found. And so this information will give me the new X, okay? And just a second. And so now I can substitute this new value of X into this equation here. Normally this will be a guess. For example, this will be 3, 3, 3, 3. You plug it in here, and then
minimize f relative to alpha, and set that equal to 0. To be able to minimize f, you can just take the derivative of f respect to alpha, set that equal to 0, and solve for alpha, which is what we've done here. In this example, you can just select the value of x1 to solve for alpha, and you will see that that'll give you a value of alpha that gives you a value of minus 0.5. So I have found the value of alpha that minimizes f relative to alpha alone, given a particular search direction with guesses on x1 and x2. With that value of alpha now, I can plug in an old guess. So in this case, the old guess I'm going to select is 3 and 3. So this gives me 6 and 6. So the new x1 and x2 is 0. Notice that if I didn't have any constraint, inequality constraints, this would have been just fine. But the problem is that the value of x1 and x2 here, which is 0 and 0, when plugged in into the first constraint equation, gives me an S1 of minus 0.2, and S1 has to be positive. The second equation here, 0 plus 0 minus 5, that gives me a value that's positive, so I'm okay. But the first constraint got violated, so I had to recalculate this value of alpha so that that constraint that got violated can be rectified. And so since I'm writing right up to this constraint and even exceeding that, the most reasonable thing to believe is that I am against this constraint. And so S1, the basic can be 0 if we think about it. So I'll set S1 to 0, and then I'll take the new value of x I came up with as a function of alpha and plug it in. So I have x1 old plus 2 x1 old plus x2 old plus alpha x2 x2 old minus 0.2. And I can now solve for alpha, and I get a value of alpha of minus 5.8 divided by 12. So all I've done is taken this constraint equation, which used to be an inequality constraint here, that was that inequality constraint, by adding the slack variable, we turn into that. But S1 has to be positive, and I violated it with my first guess. So I have to recalculate alpha so that doesn't happen. With that new alpha, I can plug it in here. The old guess was 3 and 3. So now updating the value of x, I get 0.1 and 0.1. This actually happens to be a solution to the problem. We got it done really quickly because this is a quadratic equation. But if we had a cubic or something else, we'll have to repeat this process until we're able to minimize the objective function f. And to recall, the objective function f was this one right here. How to do this in Excel? Again, go to File, under the Excel File tab, add in solver, and then you can add the solver in. And so what I'm going to do is you go under Data and click on Solver, and you want to set up the problem. And I'll go through that in Excel directly, but here are your design variables. Here is your objective function, x1 squared plus x2 squared plus 4. That's what I want to minimize. And that is subject to a inequality constraint, which is x1 plus x2 minus 0.2 greater or equal to 0. If I choose a value of x1 and x2 of 20, obviously this is not the minimum value. So let's go over there now to Excel. So here we have it. We have x1 and x2, and then the function f is 804. I want to minimize this. So I have to find x1, x2, so that happens, and I don't violate this constraint. I didn't write the other constraint because it's not going to get violated, but you can add it too. So again, go under Data, and if you don't have it yet, go to File, Options, and then go to Adds In, and then add the solver package. So all of you should be able to do it. Now go under Data, and now click on the button Solver. And so that will allow me now to minimize this cell D4, minimize, make sure you click minimize, by changing the variables B4 and C4. And I'm going to add this constraint that this cell, D7, be greater or equal to 0. And notice that this here is going to have that formula in. It's going to say B4 plus C4 minus 0.2 greater or equal to 0. And then now what we're going to do is hit solve, and hopefully you can see there that it got to that minimum value of 4 by selecting point 1 and point 1, just like we did right now. And this shows that the inequality constraint is satisfied exactly. We're writing against that equality. That equality constraint is active, is what we're trying to say. And so you could do other things with this kind of thing, but we could change the problem. We can try different things. You can formulate reports. You can save the scenario. You can outline the report, and so forth. But in general, and maybe perhaps you haven't tried it, but here under cell D7, you can see the equations are given there. Under D4, equations are given there. Fairly simple. Again, go to solver and then hit solve when done. And that will basically provide you the optimal solution using the GRG method. Let's move now to a new example here. Example 2 now is moving into composites now. So what we want to do is to determine how many plies of each of these things we want. 45, minus 45, 90, and 0. That's a question that's been asked. And we want to use, in this example, it's been told that the plate is subject to an axial force of 10,000 pounds per inch. Now notice that this is pound per inch. And so if you want to figure out the total force on a plate and the width of the plate was 3 inches, then the total force would be 30,000 pounds. If you're given total force, then it'll be 30,000 pounds divided by the width, which will give you 10,000 pounds per inch. So this is your NXX in essence. Notice how NXX has already been integrated to the thickness, and it's a stress resultant. We can also apply shear loading. It's telling that a shear loading is applied of 3,000 pounds per inch. And is asking you, and this is basically your NXY, and it's asking you that the axial strain of the laminate do not exceed 0.6%, and the shear strain does not exceed 0.4%. So that's a question being asked, and it's telling us, hey, what is the minimum number of plies I need for each of these things? And the property of the laminates were given to you. Again, you can characterize its properties using the approaches that we've discussed, and that includes includes finding out the ply angles in the stacking sequence. And we'll talk about what approaches we have that will be great for using a good stacking sequence. But the first step is to figure out what ply angles do I need. And notice there's no bending here in this example. Okay, so why don't we go to Excel and see how we went about that. I'll jump right into it. You can see here, for the example that we're discussing, that we've applied 10,000 pounds per inch and 3,000 pounds per inch in the shear direction. Again, these are force resultants, and so they're per unit width. And so if I want to figure out the total force on that edge, is 10,000 times the width of that edge, which could be 3 inches. So that would be 30,000 pounds total. If the 30,000 pounds was given to you, then you have to divide 30,000 pounds by the width of that edge, and that'll give you 10,000 pounds. And that will be what goes here, NXX. So the question is, how many plies of this do I really need? And so the way this is structured, this Excel file, you have it. You can play around with it. And E11, E22, Nu12, G12 can be found from the ASTM standards. And as you know, you have to calculate Q1, Q2, Q12, Q66. And this is in the local orientation. So this is in the principal material orientation. And then there's the invariants that we talked about, U1, U2, U3, U4, U5, in classical plate theory from last week, from the previous lecture. And from this information and the ply angle and the number of plies, I can figure out Q11 bar, Q22 bar, the Q bar matrix. And the Q bar matrix now has been, is looking now at a global orientation system. And Uh, and here is a contribution of each of these plies and the thickness to the Q11 bar and so forth. And the idea here is we want to find how many plies do I really need um, at a minimum to keep these strains to be less than 0.6% here and less than 0.4% there on the shear strain as provided in the problem statement. So the first step then is to calculate the A matrix. That's really what we need to do. I've done it here in a simple way. This is your A matrix. And notice that A inverse times the vector N of force resultants will be equal to strain. And this is true only for symmetric laminates because the B matrix goes to 0 as discussed in the previous lecture, if you recall. So what do we need to do? The design variables is a number of plies. That was the question that was asked. And the question is, what is the minimum number of plies I need to so that the plate or the structure can survive and stay within the limits that we prescribed. So here I am. I'm going to keep the number, so same number of plies for 45 minus 45, which is a good idea. I made that equal to B12. So we're going to make everything 100. Why would I make everything 100? Start very thick. It's good not to be biased about how many plies you want in a particular direction. Let's see what the optimization algorithm will tell us. Then go again into File and go into Options. Make sure you have the solver add in. And then from there, ensure that you have been able to you can then figure out the minimum number of plies, and then you want to do that with the data and then solver approach. Here we're going to set the objective function h, so we want to minimize this right here, the total thickness. That's what we want to do, is minimize the thickness. Or we can also minimize the number of plies. So actually, I can actually just make this one the number of plies, because it's the same thing. The least number of plies, then we should be okay. And so what variables can I change? What are the design variables? B12, B13, and B14. Those are the ones I can change, and that's great. Now what I want to do is to make sure that these design variables stay integers, because number of plies have to be integers. In addition to that, we wanted to have at least one ply of each. So that's why we have those design variables. Here, I need to change that because that is incorrect for our situation. In our situation, we want this strain to be less than that. So we hit OK and fix that. And then we need to fix the shear strain, which needs to be less than 0.04, 0.4%. So let's change that. So this one right there is this one. And we're done. So we fixed that. Now we're ready to solve it. So let's hit solve and see if we can get the number of plies for this design. And you can see here the bottom is going through the iterative process. It arrived at a solution, and the solution is 44 plies. It wants us to have 14 plies each of plus minus 45, 4 plies of 90, and then 12 plies of 0 degrees. And I want to point out here that I wrote almost up to the constraint. So it seems to be a fairly good design. If I went a little bit higher, 13 plies, it's not as optimal. I've increased weight. If I make it a little bit thinner, 11 plies, I violate the constraint. So clearly, the answer we got here is fairly good. And so why we got the answer we got? It's good to think about it. So I have more loading in the x direction, almost no loading in the y direction. So I expect more plies in the x direction, which is the reason I have 12 plies. But also I have shear applied, and as discussed in previous lecture, is the angle ply laminates that will help you especially plus minus 45s, help you resist that loading condition. And so it's making sense that we need that, those plies. In addition to that, we can experiment and see if we could even play with the ply angle. So what if I can modify a ply angle? Can I reduce the number of plies? And so the question then is, well, we can make this 30, we could make this equal to the minus of that, and then use this as a design variable to the ply angle there, and then the number of plies. So what we're gonna go to the solver and add that particular design variable and hit solve to see if we can get a better design. And it's gonna be working through trial solutions. The GRG is working through the different constraints that it's encountering, and then determining whether recalculating that alpha that we talked about, that the line search parameter alpha. And so why don't we look at what we got here? We got 41 plies now. And you can see that I got plus minus 33 degrees, which means that the plies want to kind of bias more towards the axial direction because I have the most loading there, yet it's finding a great balance because I have the shear loading. And so I did decrease the weight. It's not significant, so it's not a huge mass savings, but it does illustrate that now I was able to get really close to that constraint, which means that I really was able to save mass and yet get right to that constraint. So this example clearly illustrates how to use Excel in a simple way to optimize designs. Now you can use this also with bending moment. One thing you can do is turn in bending moments into force resultants, and there's many ways to go about it. Similar to when you have a bar subject to axial loading, and a bar is also subject to bending. Well, the outer fiber stresses are going to be NC over I plus minus P over A, or plus minus NC over I plus P over A. You can always come up with an axial load that encompasses even the bending loading conditions. Very similarly, you can tackle bending problems in the very same way. But we will now look into how to go ahead and solve a different problem now, a little bit different in character. This example came from a paper, and in that paper, the idea was given the laminate properties of graphite epoxy, um, determine the angle ply laminate such that the axial modulus is maximized while the laminate shear modulus is at least 25 GPa. And so you want to keep that shear modulus greater than that, and the laminate Poisson ratio should not be larger than 1. And so this is an example of how you can use optimization techniques to ensure that I get particular set of properties. And the second thing I want to mention, this came also from a book by Sever Gurdal, and he teaches optimization, design optimization. So that's really where that's discussed. This example also comes from there. So let's look at Excel and see how we can address that one. Let's try to apply it in this example. So on the data, go to solver again, and I'm going to go ahead and delete all this, these different constraints very quickly. So hopefully it'll be a quick process. And then we'll go ahead and we'll now go ahead and set the objective function as we want to find the maximum value of EXX. That was the question. So we want to maximize that by changing the ply angle, which was the question. Okay. And then in addition to that, well, first we need to make sure we just set the angle ply, so we have no 90-degree plies. And then we could just have 2 plies of each of this if you want, doesn't matter. So this is not going to vastly change your answer if you do 4 or 5. As long as you keep the same number of plies, EXX should be the same, as you can see here. And so now all we have to do is now make sure that our objective function is to, our design variable is to change this A11 value. Okay, so we want to maximize this value, C21. We want, what we want to do is keep the Poisson ratio, this Poisson ratio, less than 1. We talked about that. And then we want to keep this one here to be greater than 25 E9 GPA. That's what we talked about. So add that and then hit cancel, and these are your constraints. And so and then you can hit solve, and here it say could not find a feasible solution. Let's see. Okay, sorry about that, but I entered these values E11, E22 incorrectly, so I have updated that. And my plan, and another thing I want to point out, is good to start, if you're going to vary ply angles, it's good to start at 45 degrees, because it's a good happy medium between 0 and 90, and then let the software decide how to get there. So we're going to then do data solver and then hit solve again. And again, I apologize for that error. And hopefully we'll get to the solution. And yes, we got it to the solution, plus minus 36 degrees. And the GRG method got us. And you can see here that the Poisson ratio constraint was hit, is less than 1. GXY is greater than 25 GPA, and I have maximized EXX. We can check that by changing this angle to 30, and you can see that EXX, I violated the Poisson ratio, for example, so that's not good. I can try 40 degrees, and you can see here that that's not as good as 36 degrees in terms of EXX. I want to maximize EXX. So 36 was the best answer to the problem for what we're looking for. And so again, another way of using optimization is to maximize the properties that you really want. We want to maximize EXX, and so that's another way to exploit the GRG optimization method. So now what we're going to go to another problem. In this problem that you're going to be solving is a design of a cylinder wall. And the design of the cylinder wall is a pressure vessel of a wall that's a 20-inch in diameter, pressurized to 500 psi. The laminar properties are given here, and the cylinder must take also a torsional load of 300,000 pounds. The strain in the y direction is limited along with a shear strain to 0.5%. And we want to have a ply schedule that has 0-degree plies, 90-degree plies, and an equal number of plies, A and minus A. So we want to also have half the number of plies in the 90-degree compared to the 0-degree. So the question is find A and the number of plies for each ply angle to minimize the total wall thickness. So the way you want to approach this is that you have to calculate NXX, NYY, and NXY. For example, NXY can be calculated by dividing 300,000 pounds by 2 pi r, because you want to get that in terms of NXY, which is pounds per inch. And so that'll take care of that. How to deal with NXX and NYY. So NXX is along the longitudinal direction of the pressure vessel. So that should be, that's going to be P times R, basically. P times R divided by 2 in the axial direction. And then in the hoop direction, NYY is going to be P times R alone. And that will give you NXX and NXY. Now, it may be confusing to you that we are discussing the NXX to be P times R divided by 2 and NYY to be P times R, but you have to realize that the stress in the longitudinal direction is P times R divided by twice the thickness. And the hoop stress is P times R divided by T. So stress times T gives you the value that we're really looking for, which is nxx or nyy. So please go ahead and set up the problem using the Excel sheet that was provided to you, and then hopefully we can get it done. But in the meanwhile, I challenge you to solve this problem, and I think it'll be a lot of fun. I think optimization is great because that's the whole thing of composites, is to come up with these ply angles that will really optimize the design for your needs. So let's move now into a new topic, and that is material selection. And so for material selection, what we're looking for there is what materials can I select for my design, and how can I tackle the problem from that perspective. So we're going to go into something called the choice problem. So given n choices of materials, we want to choose one that will minimize the objective function. And that's a very interesting idea. You could have 20 different material systems. Which one you should select to be able to maybe minimize objective function? In this case, could be minimize the weight. Normally, this will require conditional statements, but this will be very inefficient. Instead, we're going to use the idea of binary design variables, where integer values take the value of 0 or 1. So say we have R design options. We can define our binary design variables, x1, x2 through xr, with one design variable corresponding to one option. So if I were to select the ith option, then xi is 1, and otherwise otherwise it will be 0. So the idea is, how can I accomplish that? How can I select one option out of R options? So one thing I can do is I can create an equality constraint that says x1 plus x2 plus x3 all the way to xr is equal to 1. This will force me, since x1 can be either 0 or 1 binary, it forces me to select one of these options. If x4 is 1, then everything else has to be 0 because I added them all up, and that has to be equal to 1. So this is called a choice problem, and I'll illustrate that with a geometric problem. And this is how this choice problem works, this particular problem. Given a unit area, so given a unit area, you have a square, a triangle, or a circle. All of them have a unit area. So let D be the side length for the square, for the triangle, and let D be the diameter for the circle. Okay, so we're forcing the fact that these are going to be unit areas, and that in this case, the square will be an area of D squared, the circle will be pi D squared divided by 4, and the equilateral triangle will be square root of 3 D squared divided by 4. So just using geometry. What we want to do is determine D. So we want to find D, which you know the answer. You can solve for D, but the idea here is to figure out D without having to do anything yourself, using GRG, and let GRG take care of it. But the question is determine D, but also we want to find which of these three geometries leads to the minimum perimeter. So which of these geometries will satisfy the unit area approach, the unit area question, but also gives the minimum perimeter? You probably know the answer by now. So for the square is 4D, for the circle is pi D, for the equilateral triangle is 3D. Now, notice how we're forcing us to choose one of these three. So that becomes a choice problem. So how can I put this into a optimization problem? So we want to find D, and either triangular, circular, square makes that happen. So minimize the perimeter, and then we force it. We say, okay, this is equal to x times 4D plus y times pi D plus z times 3D, because I want to minimize the perimeter. I'm adding them all up. And it's subject to the fact that I have the area of each of those geometries times x times y times z, all them added up minus 1 equals 0. The third thing I'm doing here is we're implementing a constraint. And the constraint is that x plus y plus z equals 1, and x, y, and z are binary. That's forcing me to make either x is 1 and y and z are 0, or y is 1, x and z is 0, or z is 1 and x and y is 0. So I'm forcing one of these to be chosen. And that automatically means I'm choosing which is going to give me the minimum perimeter, but it's also forcing the constraint of this area being equal to 1. So we could implement this in Excel very simply. And so I'll start with a diameter of 20. That'll give me an area of the triangle of this much, the circle of this much, and the area of a square of this much. 20 squared is basically 400. And the circle is pi or d squared divided by 4. And so then the choice, I have x, y, and z, and the choice is 1, 1, and 1. The perimeter, given that d value, gives me a triangle, a perimeter of 60. That makes sense because the triangle, each side is 20, so that gives me 60. The circle is 2 pi r or pi d, and then you have the square, which has 4 sides and gives me 80. And so then I add all this up, but I'll multiply this area times x1, this circle times y, this square times z, and I also do the same thing for the perimeter. And I'm going to force the optimizer to target cell E7, which is minimize the perimeter. That's what I want to do. I want to minimize the perimeter. But by changing which cells, I want to change B, the diameter or the characteristic length for that geometry that we discussed, D. And I want to choose D4, D5, and D6. I want to be able to make that either 0 or 1. And I'm going to force it by setting D7, the summation of all these three, D7, I'm going to set that to 1, so that's a constraint. And B7 is being chosen to be an area of 1. We said that. And then we also want D4 through D6 to be binary. So that forces this to be 0 or 1. And so let's go and figure out how to do it in Excel. So here's Excel. And what I want to do now is to figure out the diameter or the characteristic length that will give me the area of 1. That's what I want. And I want to make a choice of which one gives me the least perimeter. So not only I have to minimize the perimeter, but which one gives me that. It's a very complex problem, but we know the answer. And we can go to the solver again. And like I discussed before, all this has been done. We want to minimize E7, which is a perimeter. We want to change these three values, and we also want to change the diameter. So those are the design variables, such that the choice D7, that the addition of these three gives me 1. So it's forcing me to choose one of these. And setting each of these as a binary value. And then the area has been set to 1 per B7, and you can see that here. And then we hit solve and see what happens. You can see here the optimizer is doing its work. It found a solution, just a second here. And now I have pulled up the Excel sheet, and you can see here the optimizer has found the proper diameter that gives me the area of 1. You can see here you selected the circle, and the circle is the one that satisfies that constraint plus gives me the minimum perimeter. So you can see here quickly how we're able to solve the problem in a quick way. So the circle is the only one that gives me a unit area and the minimum perimeter. And as you can see, the optimizer selected y to be 1, x0, z0. So it discarded those two options and it's stuck with with a circular geometry. So then the question becomes, how do I apply that to composites? So I have 4 different materials, say. I have their properties, and I have their thicknesses. And I want to be able to figure out which material is the best for my situation. We want to select from the following ply angles as an example. That's one thing that we could do. We could select the number of plies of each of them. And then we can subject the laminate to be less, we could have the strain to be limited in each of these directions, and then force a selection of all this stuff. Ply angles, how many plies I want, what material, which material system I should select. And so I'm going to open Excel very soon and show you how this works. But in yellow are the inputs. These are the design variables, okay? And notice here, we're still talking about symmetric laminates, and we're talking only about in-plane loading conditions. That's important consideration here. And as you can see here, I have 4 material choices, and the 4 material choices are these 4, and I'm going to assign a value of 1. And these are going to be your binary variables. And I'm going to make sure that I select 1 by adding all these to 1. I'm going to force it to add up to 1 in the optimizer. And I'm going to make sure the binary value is, these are binary quantities, either 0 or 1. So that will force it. That will definitely force it. And then the second thing we want to do is figure out the number of plies. And what we want to do is minimize the total sum of the thicknesses, and that will force me to find the optimal number of plies I need. We also, instead of doing very discrete number of plies, we could have made the number of plies also arbitrary. But for simplicity, we stuck to 0, 15, 30, 45, 75, 60, 90. And then the optimizer can select, hey, I want this number of plies at 0, this number of plies at 15. So this could be improved. But for now, I think this should work very well. We've made everything equal 20s, everything 1, so there's no bias about where to go. And then we'll then execute the approach. Note that if we examine one set, so just one area of this Excel sheet, since it's huge, the 0-degree Excel sheet will focus on that. This one here represents the number of applies, and we made it integer as a constraint also, so I don't get a half number of applies. This is your binary choice, and this is a constraint here that we've added so that this addition here, which is a material ID, corresponds to the material ID, that I select one of these materials. And again, MID, the material of choice is one of these 4. And so if I get a 1 here and 0s here, I'm selecting the first material system. And so, again, that's the approach that we've used. And so I'm going to run an example now here in Excel in a minute. But let's examine the situation where I have strain. I have loading in the Y direction. And the loading is 20,000 pounds per inch, only in the Y direction. So when I run the optimizer GRG, and I put a constraint on the strain not be greater than 0.6%. So if I use a GRG optimizer, what I find very quickly is that I only get 90-degree as a solution. 90-degree plies, and I need 20 of those plies to make this happen. And it's telling me which material system is the best. So that makes sense that I got all 90 degrees because I only have loading in the Y direction. In the X direction, I'm applying 10,000 pounds. And so again, no more than 0.6% we want. And here, I had 20,000 pounds per inch. And this one have 10,000 pounds per inch. So what does that do to the ply? So when we run the optimizer, we get 0-degree plies for that material system and only 10 plies. So 0 degrees and 10 plies. So that makes sense that it got cut in half from this situation, 20,000 pounds down to 10,000 pounds. And it makes sense it went to the 0 degree because that is a primary loading direction. And so if I were run the optimizer again, you could get even 8 plies and at 0 degrees and 1 pair at plus minus 15 degrees. That's also a valid solution to the problem. And so we can run another example here. So here I have shear loading applied only, and I want the shear strength to be less than 1%. NXY is 5,000 pounds per inch. If I run this example, I will get just IM7 8552 unidirectional and 6 plies at 45 degrees. That makes total sense because the 45-degree ply is the one that will resist pure shear motion. And so the optimizer was able to get to that state. Now let's look at a little more complicated problem. And for this one, I have 10,000 pound per inch, 5,000 pound per inch, and a shear of 3,000 pound per inch. And I want to keep the strains less than 0.6% and the shear strain less than 0.1%. So the question is how to establish this. And so we can go now and study that, how we approached it. And so what we have here is the setup. So we have the material properties, and these ones are binary. So we will select one of these properties. And here's where we input, where the solver is going to select one of these properties. And the way we accomplish that is by ensuring that if, for example, this parameter E10, we want E10 to be an integer, for example. E10 has to be an integer. And we also have the parameter that it needs to be equal to 1. So that is the approach we're taking to facilitate this approach. We also have, I'm sorry, what I meant to say is that F10 should be no more than 1. And so that's what we have set there. And that forces this summation to be 1, which causes one of these to be selected because we have a binary for all that. So all the G's, all column G is binary. As you can see here, G is completely binary, which forces in groups of 4, we are selecting one of this to be selected. So the optimization code is fairly straightforward, and the next step is to just go ahead and solve it. And it works really well. And so you can let the optimization problem go through, and it will continue trying to solve the problem. And what we find is that the optimizer finds that we need 4 plies at 0 degrees, 2 plies at 90 degrees, 3 plies at 30 degrees, and 3 plies at 15 degrees. And it's mixing all kinds of material properties, but you can make it all the same by forcing this one to be IM7. So multiple solutions may exist. In this case, it was based on the initial choice of the design variables. And note that there are more plies oriented in 0 degree, 4 plies compared to everything else. And the reason is because we have higher loading conditions. In the Y direction, we have half the load, so 2 plies there makes sense. And since there's some shearing going on, then the optimizer has to come up with some angle plies to be considered. So at the end of the day, what we find is that we need 4 plies at 0, 2 plies at 90, 3 plies of a pair of plus minus 30s, and 3 pairs of plus minus 15, with a total thickness of 0.14. So that's pretty outstanding optimization approach. If we hit the run button again, what we find is we get a slightly different solution. And that's the whole point, is that the optimizer can give you different answers if you keep looking for, if you keep using the previous guess as the initial guess. Now, as you can see here, the total thickness is 0.14, so I haven't really done anything to decrease weight. And if you keep hitting the solver with this, you may get different answers, but for the most part, you will do fairly well in optimizing the design. If anything, this gives you a design guideline of where to go with your design. So how could you use this in real life? You have a finite element model. The finite element model can give you information on which NXX, NYY, NXY you have in a particular area. So you can use that information to then run your optimization to figure out what ply angles you need in that area. Again, there's Hypersizer, many other codes, but this is a good approach to kind of get a feel for what's going on. So we let it run in Excel while we're doing that work. And what we can see is the solution that came out is that we don't need any plies at 0 degrees, nothing at 90, nothing at 45, and nothing at 30. So, but it wants us to use 15, 60, and 75. 15 at five of them, 60 one of them, and 75 three of them. Now, it's interesting because that's different from what we got before. It wants us to use IM7, AS4, and so forth. And what you see here is that the thickness even got shaved a little more, 0.138. And notice that we ran against the constraints, so we did a really good job there for this problem. So again, there's multiple solutions to be found. We could even hit the solver button again and see what will happen. And so in-plane laminate design, multiple materials in one laminate, while feasible, may not be an appropriate design choice if materials are incompatible. An optimizer can be reformulated to limit the choice to 2 compatible materials or just 1. Sometimes resolving the optimization problem using the previous found solution as the initial condition can lead to new interesting laminate stacking sequences that are more optimal. And I recommend never settling for one solution, but looking at the whole design space and see what makes sense for your application. Later on, I'm going to discuss what are good design choices when it comes to optimization. You should limit the stacking sequence. You don't want a lot of angle plies next to each other. So plus minus 30, plus minus 15 next to each other may not be good, since this can lead to some matrix cracking and delaminations. So here I ran another example, but if we use the same solution as this one and rerun it again, suddenly we find that IM7 is a good solution to the problem. 9 plies, 2 plies, 2 plies. Again, now I reduce the total thickness to 0.13, even a more optimized design. And I do have more plies oriented towards the 0 degree because I have a 10,000 pound load. And at 75 and 45, I have some amount of plies to account for the shear loading and the loading in the other direction. And here we ran another case, and you can see here quickly that the results look different again. So I have at 0 degrees, I have 3 plies. Then at 30, I have 1 ply, and 15, 3, 60, I have 1, 75, I have 2, and the total thickness comes out to be 0.132. 0.132 there, and the strains are right up against the constraints as we discussed before. And so again, you can continue, for example, hitting solve again and see what will happen. But the idea is that you may have different solutions every time you do that. And so, for this example problem, what I recommend is using the data that we got in the previous example here. You can then come up with a ply angle distribution. So I say 0 degree plies in the outside, plus minus 45, 0 degrees, plus minus 75, and then 0 degree ply in the symmetry plane, keeping the plus minus 45 and plus minus 75 degrees apart, letting the 0 degree ply to be in between to prevent any through a thickness matrix cracking that can propagate from one angle ply to another. It also, this ply distribution seems fairly good. We're not, I'm not seeing a significant issue with this design, but again, you should check for your problem of interest if you need to do something with sacrificial plies in case you have some sort of impact damage potential. Then you want to add a few more plies on the outside to protect the structure even more, and maybe some fiberglass. So And then you can keep running this server and this solution with the server, and you get 7 plies at 0 degrees, 2 pairs of plies at this, 2 pair of plies at this, 1 pair of plies at this, and the total thickness is 0.13. But this has too many angle plies, and it's hard to make symmetric. So what if I want to design laminates for bending loads? So consider the problem of minimizing the weight of a symmetric, simply supported plate subject to a uniform load distribution. The deflection of the center, I don't want that to exceed a value of D. And so the design variables are ply angles. And then you also have the number of plies in the design. So recall that the solution for bending stiffness or for the deflection at the center of a plate can be found to be this. And this was discussed in the previous lecture, classical plate theory, which we examined the solution for this. Q is a uniform load in this example. M and N are from this summation symbol. And then we have D11, D22, that comes from the D matrix. And then the alpha is defined in terms of M, pi, and so forth. The complication here is if you want to implement something like this for this particular situation, is that the maximum deflection depends on the bending stiffness matrix. And so, but the bending stiffness matrix depends in the location Z, and is cubed also. So for symmetric laminate, I could just look at half of the plies, so that's N half right there, and I've simplified it a little bit, but it makes it a little bit difficult because I cannot have empty plies in between. And so what we're gonna do is we're gonna modify this expression and apply a binary variable V, VK, and that's going to ensure that we don't have empty plies in between. And let me illustrate what I'm talking about here. So this is a midplane of the laminate, and there's plies that go 1 through N half. So when I was just looking at the A matrix, just stretching of the membrane, symmetric laminates, we didn't have that situation because the location of the ply angles didn't matter through the thickness, since the A matrix does not depend on the position of the ply. But it does matter when you look at the bending situation where it depends on the D matrix, the bending stiffness matrix. It matters because you could have a situation where you have empty plies in between. And in fact, the solver is going to try to have empty plies in between because that minimizes weight in the first place. And that's how sandwich structures work in the first place. But if I want to laminate, and I don't want to have empty spots in between or have foam in between, then you have to start thinking of how to make sure that the inactive plies are getting inactivated from the outside. I don't want to have a situation where I have empty plies here, 1, 2, 3, 4. So we need to come up with a very clever way of doing it. And the way we did it was to modify the D matrix so it's calculated with this V binary variable. And the approach that we're going to use is to minimize the summation of all these V's. Notice here how if I minimize the summation of all these V's, what I really get is what is the minimum number of plies I really need. And you can see that here. We want to minimize the summation of all these V's because that gives me the minimum number of plies. And then the second thing I want to make sure is that this value here, V4, be always greater than V5. I always want to make sure of that. So if I can make sure of that, then I'll never have empty plies. For example, if V3 was 0, somehow the optimarshal thought there should be a 0 there, then suddenly this constraint is violated because then V2 is 1 and V3 is 0, but then V4 goes back to 1. So this particular constraint here gets violated. And so we want to make sure that we subject we apply this inequality constraint, and on top of that, for the current problem that we're analyzing, we want to make sure that the deflection is no greater than a value of D. So the idea then is, what is my design variable? The idea is to find which of these should be 1 or 0, and we know that it needs to be consecutively 1, and it cannot have 0 in between because of this constraint. And the second question we want to find is, hey, what ply angle should I have here to be able to make this work? So some clever ways can be used to optimize ply angles. That problem can be solved fairly simply. Here's an example problem. We want to determine the minimum number of plies and ply angle alpha, which will have the following stacking sequence. So we chose a particular stacking sequence, and alpha is the only thing that can be varied. The composite material will have the following properties, and what we want is that we don't want the center deflection to be greater than 1 inch, and we want the plate to be 5 inch by 20 inch. So these are the constraints that we're talking about here that we would like to examine. To tackle this problem, we're applying a load of 1,000 psi across the whole face of the plate. So the plate is simply supported with 1,000 psi applied pressure. A is 5, so one edge of the plate is 5, the other edge is 20. And what we want to do then is to calculate the deflection. And the deflection, what we want to do is keep that less than 1. And so to accomplish that, we're going to have to figure out clever ways to apply this approach. And so what I want to do is make sure that theta is the only angle we plan to change, and that's going to propagate all the way through the stacking sequence. The deflection formula I discussed is really for D16 and D26 that's relatively small. So you need to ensure that those are a fraction D11 for this example for this to work out. And what we're doing really here is calculating D11, D22, D12, all this stuff based on this formula and using the Q bars. And I'll show you later in Excel sheet how that's done. But we're doing for half the stacking sequence and then multiply by 2 since it's symmetric. And then we've done a little trick. So local midplane location is 1. And what we want to do is start adding or removing plies. And the constraint is going to be put in here to ensure that we don't have a situation where I have empty plies in between. So this is really where the magic happens. These are the ones that could be changed from 1 or 0, but we don't want zeros in between. So the constraint becomes to ensuring the C18 through C45, that those are always greater than 0. And this formula that's in here is to basically ensure that this number minus this number is always greater than 0. And if it's not, then it's not going to allow to put any negative 0 plies in between. And again, we're going to also come up with a ply angle here that will propagate through. And so the initial guess is that all the plies are active. We'll make them all active, and we'll figure what happens next. And we're going to have some minimum number of plies just to start, and then let the algorithm, GRG algorithm, select which one should be active. And when you run it, it finds out that I don't need these outer plies. I don't need plies 17 through 24. I can survive with the plies here. And it finds that 0 degree makes the most sense. That I don't need 45 degree plies. And it came to 0 degree plies. The solution is that 32 plies are needed. That's all I need. I need 16 plies for half of it, so 32 total. The solver selected a preferential direction of plies oriented in the 0 degree. I want you to think about that. Think about this rectangle 5 by 20 has a distributed load of 1,000 psi. So does it make sense that the ply should be in a 0 degree orientation? And I think what you're going to find is, yes, it makes sense. More plies are required along the 5 degree compared to the longer side in order for us to get a minimum number of plies. So if you think about it, if you buy an IKEA bed with those slats, and if you're to lay on the bed, you want those slats to be oriented so that it's on along the short edge of the bed. so it can take the load more uniformly. What we find is that the center of deflection is near 0.93 inch, which is not quite 1. So you could probably solve again. And what you get is that you get a value closer to 1. And then the ply angles got switched around to 20 plus minus 25 degrees. So he was able to figure out a better solution that got us closer. So again, hitting the solve button sometimes gets you closer to the solution. So this is a little bit of a messy spreadsheet, but I think it's going to help us understand how this was done. Like, what if we select a square plate? Then what is the optimal ply angles I need? And so here you can see this constraint here is that B17 minus B18 right now is 0 because the two consecutive values are 0. But let me illustrate for you. If I make this one inactive, I'll have a -1, and the constraints are written so that all this has to be greater than or equal than 0. So you cannot have an empty ply in between. That forces this to be 1, okay? And so we're going to figure out which ply should be active. What we want to do is basically figure out the deflection, and we don't want the deflection to be greater than a particular value. So that's what we're trying to accomplish here. Again, the same problem, 1,000 psi with a square plate in this case. And then here are the equations that were used. Here is where the d's were calculated, and then plug it into this equation using this approach in Excel. I won't go into great detail because I'll provide you this Excel sheet. But what we're going to do now is to go ahead and do the data and the solver approach. And let the solver take care of it. And I'll hit the solve button. But before I do that, B46 here is what I want to minimize. I want to minimize the number of plies. So I have put minimize by changing the variables, and I want to change any of these variables and then the ply angle as well. And I want to make sure these are binary, and then they're subject to the constraints that all these have to be greater than 0. Otherwise, if there's an empty ply, I'll have a negative value. So I'm trying to keep everything filled in between. And also I want to make sure that I can actually get a good solution to this problem. So we'll go and hit solve. And as you can see, the solver has completed the solution, and it has found that I can get close to that deflection with a 45-degree angle on that square plate. And then I don't need all these plies. All I need is the interior 11 plies, and that's the stacking sequence that I need. So again, you can play around with this data to kind of figure out whether things do make sense. To me, this makes sense if I have an edge that's basically the two edges are equal, then I think 45 degrees is a good balance to try to pick up the load for this pressure applied. You could hit solver again. So again, you can hit solver again and see what will happen. So going back, we could switch around and make it 20 by 5 inches instead. And so now you will notice I need 90-degree plies. And again, why it got rotated is because I need to have 90-degree plies along the short edge. And that's why that happened. But it's the same solution as I found before, but rotated 90 degrees. And what will happen if I use a square plate? I already showed you that the solver is going to try to give me plus minus 45 degrees. It is going to try to minimize the number of plies. Another solution we tried gave us 24 plies, but those were just 0 and 90s. And again, that's perfectly acceptable. So it is possible to use GRG methods to optimize the deflection of a plate subject to transverse uniform loading, but always care is needed to ensure the results are meaningful. The considerations for bending and twisting, D16 and D26 are usually non-zero, but this can be made close to 0 by arranging plies, and that's actually beneficial. Except for very thin laminates, if you stack minus A ply next to A ply in thin laminates, you will get that. Neglecting D16 and D26 in the flexural response can work out if you have this to be true. If this is less than 0.2, then you can neglect it. And there is this paper that goes into great detail by Nemeth. What about lamina design? What if I want to design a lamina? I want to come up with a new material system. And Dr. Scott Peck, very well known in the area, has written a paper. But what if I want to do that? I want to come up with this design lamina engineering constants to minimize weight. So that means coming up with a new fabric system, a new metric system, something innovative that helps you minimize weight. So you basically really, before doing this, it's important to understand the inequalities that must be added to ensure that the lamina you're working on is physically realizable. The stiffness C has to be positive definite. And there's this paper, Physical Bounds and Material Properties by Dr. Scott Peck. And if you're listening to this video, thank you for being one of my great colleagues. You know, like the passion you have for composites is amazing. So I recommend you read this paper. Material design, material selections and tailoring of stacking sequences and total laminate thickness are not the only way that you can exploit composites. You can come up with new materials, like I said, that can achieve optimal designs by coming up with unique elastic and shear and Poisson ratio data. However, one needs to make sure that whatever you come up with has to be physically realizable. And elastic properties have to be such that the compliance matrices are positive definite. And so the compliance matrix is positive definite if every eigenvalue is positive. And so if, and what that means is that if I take X and X is an eigenvector of A, and X is not equal to 0, that doesn't matter what eigenvector you choose, that for every positive eigenvalue, that this multiplication has to be greater than 0 for all vectors of X. So while the eigenvalues for a 3D compliance tensor could be determined to establish physical bounds, we only have to really show the derivation for 2D since we're looking at the classical plate theory, but that can be applied to 3D. So the compliance matrix looks like this. The eigenvalue problem looks like this. And all you have to do is find the roots of this equation. And then after you find the roots to this eigenvalue problem, you can then now establish the bounds we talked about. Like lambda, this has to be greater than 0. This has to be greater than 0. And so that forces us to say that this has to be greater than 0. And it forces us then to come up with unique relationships about what has to be greater than 0 and what Poisson ratios you can have. Using that information in 3D, you can come up with even more bounds. You get 6 eigenvalues now, and you can establish those bounds fairly readily. So let's go to a new example problem. And the idea now is come up with ply angles, but also what E11, E22, and G12 should I select to optimize this design. Now for 2D, I have to satisfy this relationship as we discussed here. For 2D, this is the relationship we need to satisfy, and that's what is shown here. So that's a key here that needs to be considered. You can design new materials, you can come up with that, but you have to make sure they're physically possible. So here's the Excel sheet that we're talking about. This is what we're going to be using to figure material properties out. So I want to come up with a unique E11, E22, and then I want to come up with ply angles and perhaps even the angle. Given the loading conditions, we want to make sure that the Poisson ratio, all this stuff works out, that I'm not making stuff up, so it's physical, and we want to solve the problem. So in the solver, what are we trying to do? We're trying to minimize the thickness. So the thickness is given by this one right here, or this one, I'm sorry, total thickness. And we want to change the variables E11 here, E22, and then we want to change nu12 as well. So we're changing all these three. And then the integer B12 through B14. So these ones right here, we want to keep integers. And then we want to make sure that the physical constraint here be achieved. So that's what's done there. And then we also want to make sure that we are trying to figure out that the strains, I want to keep the strains also low. So I'm going to try to keep them all below 0.5%. That's what I'm trying to achieve there. So we could hit the solve button again right here, and then try to solve this, find the solution to the problem. And so here we want to minimize weight, and we are able to figure out how to approach this problem using Excel. I showed you how to do it. And when you run the optimization, it comes up with this moduli, which is unique, and then with these ply angles. And then it hits some of the constraints, but not all. And there are many ways to hit that constraint. You could, for example, one possible solution is to have um, these type of ply angles, but then it rides against these constraints really closely. And again, you're trying to minimize weight, so it may not be always the most optimal, but you're trying to find the optimal solution for the design. So this will conclude the optimization lecture, and I hope you enjoyed it. I think what is a lesson learned today is that, you know, quasi-isotropic laminates 0 plus minus 4590, which provide you nearly isotropic materials in the plane of the composite, may not be the best choice if the loading environments could differ from one edge to another. So if NXX, NYY, NXY are such that you may, quasi-isotropic laminates may not be the best choice. It may be that you want to tailor them. And what I've shown you today is an approach to doing that. There's a lot of codes now that can give you that information, but I think there's a lot of value in you kind of playing around with this stuff so you can build an intuition. For example, if I have a loading condition of 10,000 pounds in one direction, but very limited amount of load in the other transverse direction, you should be able to come up with a ply stacking sequence that makes sense that will take that load. And then if I add shear, then also you may want to develop the intuition where you don't need to be using optimization codes all the time. But in the meanwhile, there is a lot of value in playing around with these codes and try to understand what the codes are trying to do, which I think is a benefit of what we're trying to do in this particular lecture. I hope you enjoyed the lecture, and I hope you stay safe, and thank you for listening, and have a great weekend.